Okay, today we're going to be addressing barycentric coordinates, and if it's simple enough, we might even be getting to researching WHFast for once. So, good news. Okay, so yeah, barycentric isn't done yet, so time to ask Gemini. What prompt should I give? Let's say, how do I convert between not that. Let's ask, what is barycentric coordinates, and how do I convert to and from inertial? Yeah, Gemini. Okay, what are barycentric or coordinate system relative to static or universal? Okay. So I think we need to. Yeah, I think we're gonna need to, yeah, we're going to need to calculate the origin is center of mass, so our body relative to Bary body and the body relative to the barycenter. Okay, so barycentric coordinates are the mutual center of mass. Can we determine this? Yeah, okay. So if we go to our body rel Bary, the body relative to the barycenter plus. Okay, so what I'm interpreting this as is we're adding the inertial and we're adding the body relative to the barycenter. Interesting. Yeah. I mean, this is reversed, weirdly, but I guess that makes sense. That doesn't, but okay. The basis, so, what? So basically, to convert, let me verify this. So basically, to convert to barycentric coordinates, you move everything such that the barycenter is at 0, 0. It's at 0, 0. So, but then how do you retrieve? How do you retrieve inertial coordinates? Yeah. Okay. Okay, so R is inertial. The position of the object, R object relative to the barycenter. Object is in the planet relative to the barycenter. So barycenter is at 0. The Earth at position 100. Spaceship's at 105. Yeah, to retrieve the Earth-centered inertial position, we just do this. Plus 5 relative to Earth. Okay. still called inertial because you're shifting back to Earth. Up down is called the body-centered frame. Okay. Because if the barycenter is at, say, is at 5, star at 0, and planet at, let's go for 100. 100. Barycentric would make barycenter 0, star -5, and planet 100. Planet 95. Okay. Subtract the planet. Okay. Oh yeah, so you're basically being forced, you're losing some form of information as it started. Okay. That is what's happening. Okay, I think that's clear. I guess we're just gonna use the star for this. So, transform.cpp. Okay, going down like there's about it, right? There we go. Void barycentric to inertial pause. So it'd be const particle store particles and particle store PB. Yeah, I think so. So first we're gonna have to determine the barycentric position. So vec3 bary pause double total mu equals 0, and pragma will be parallel 4 size ti equals 0, as then particles dot test dot value or particles dot n plus I, we bary pause plus equals particles dot positions index I times particles dot mu's index I, and total mu equals plus equals particles dot mu's index I. Okay, and now I have to throw in the reduction. Plus colon, you get bary pause and also total mu. And I'm just gonna say bary pause, and now we just have to divide this by total mu. Okay, that looks good. Now, what we have to do is throw in another pragma. Bro, I don't need you to form. What are you doing, girl? Anyway, 4 size t equals 0, I understand particle dot n plus I, and we say particles dot positions index I minus equals Bary pause. And I think we're just gonna be, yeah, let's take this generic because I'm about to copy this a billion times, so the variable is, yeah, okay. Bary, okay, what's there? Use of undeclared identifier Bary pause, yeah, here, okay, yeah, there it is. What is it? No viable overload. Wow, oh my god, that's position index I? What are you doing? Oh yeah, fair. Oh yeah, I'm trying to edit. Okay, good thing I have const. That's just the error. Yeah, the equals particles dot position index I minus Bary. And now you can do this. And now you are going to be yanked again. Well, and the only change here is velocities for all three of these. And you're going to have it, I'm just going to have a similar thing for acceleration. Okay, and now finally I can just, okay, so now we're gonna have to deal with inertial to barycentric. And yes, we have lost all our relative position information. We're going to choose a body for it to be relative to. Yeah. I'm going to assume we want it near the star if you'd want. Assume you want it near the star, so I guess you could. But like, sure, I guess. Yeah, there's a reason that those headers are in the code and rebound. They're definitely being used. So I'm just gonna do some basic stuff in here. Particles, PB, and actually no, this one's const, and this one's particle store. So vec3 Bary, no, we don't need Bary actually. The formula here is we subtract some random position from everything. It's literally just one loop. Program will be parallel for size t I equals 0, I just stand particles dot n plus I pb dot positions index. No, you do particle dot positions index I. Yeah, and of all of these, use are strict. Yeah, this is not fun. Let me just put these back in. Yeah, this is gonna take a bit. This code is gonna be very important for performance. And if I continue down here, yeah, these are just gonna be strict. And okay, that's done. Now we can just go pb dot positions index I minus PB dot position to next 0, and no, I'm just gonna call it, put star equals PB dot position to next 0, and I'm going to call star. Okay. I'm optimizing for copy paste ability here. And now if I go do this, val, and it's going to be a very similar thing. We're going to have to set all 3 of these to velocities. Continue copying and acceleration. And let's wait until this happens. Okay. Coordinate conversion done. Well, that's a funny consequence. Oh yeah, and off camera, I did set the whole thing to MPL. Final code. Wonderful. Bugs. Okay, what is the error? With the code dot Barycentric and a little pause things into the I swapped names. Oh, fine. That's fine, I guess. Yeah, that's just naming something. It's not that severe. Inertial to barycentric. I'm gonna have to do this, or all of these. Okay. Inertial to barycentric. I'm gonna drop the const here and add one here. And you know. Okay. Okay. Yeah, so great. I errored this whole section. Yeah, okay. Yeah, you know, I'm just gonna redo this whole section. I guess I'm just gonna delete this and copy paste it. Paste it again. Okay. This is not great. So, yeah. Yeah, just give me the fixed code. Just give me the fixed code. Yeah, I don't want to be trying to. Give me the fixed barycentric block. No comments or anything. Yeah, I do not want comments in this thing. It's gonna make it too clear. Yeah, this is. Yeah, okay. Yeah, I'm just gonna paste this. Oh, look, it even maintained my formatting. That's good. Okay, yeah, this is great, actually. Okay, yeah, so conversions are complete. The issue now is, how do we convert this back into Jacobi? But sorry, no, not that. How do we do WHFast, which is going to be the second easiest integrator to implement? WHFast. Yeah, I have this paper for WHFast. I think I might have had this. This is the Hernandez paper, but if I go to... This is the wrong paper, actually. WHFast. Okay. I have it here. View PDF. Thank you. Now I have a giant paper I need to read. This is great. Great. Okay, so WHFast, I know this sort. I'm gonna ignore that. And let's read this. Okay, so background. The Hamiltonian can be written as the sum of kinetic potential coordinates as this monstrosity. So yeah, pi squared over 2 gamma I. Means the sum of the gravity. Yeah, sum of gravity, yeah, basically. Minus the sum of gravity. You have this section of Jacobi coordinates here. Hamiltonian splitting in terms of the conjugate momenta. We only rewrite the kinetic term and keep the potential expressed as Cartesian coordinates. Yeah, okay, so I don't see much of a difference. I only see a prime. I don't know what the difference is. Note that kinetic term is still diagonal. Either no cross terms involving pi, pj with I equals 1. Gemini, please help me. Delete you. I don't care about you anymore. Decode this and give me a decent summary of the math in there. Yeah, okay. Okay, great. Okay, yeah, okay, so core Hamiltonian splitting, so basically, yeah, it splits into the Kepler and Hamiltonian, or interaction. Dwydom-Holman symplectic integration. I said symplectic, it's symplectic. Continuously calculating everything, it alternates. And then Keplerian orbits and then kicks. Yeah, that's what it does, basically. Transforming back and forth between standard Cartesian coordinates, Jacobi coordinates, whereas complex linear algebra carefully re-engineer the linear transformations, getting Burr's law, truncation errors in algorithm bias, round-off errors accumulate linearly over time. Brouwer's law states on an ideal unbiased simulator, error energy is about a random walk, growing much slower, proportional to the square root of time. Okay, so now we have, instead of your linear drift, it's square root. Okay, I'm gonna read through this. To drastically reduce the truncation errors, implement symplectic correctors. It's aka the giant table. Okay. So convergent fewer CPU cycles. Okay. Okay, are there formulas I can actually implement in code? Yeah, because I do need that stuff. Yeah, okay. Compute cumulative masses, Jacobi masses. Okay. So, dictate that these exact algorithms to prevent floating point round-off accumulation or attract the center of mass everything interior to planet I. Okay, now I have to have this. So, yeah. Okay, this is interesting. The issue here is I already have the code. Have the Jacobi transformation code. Okay, having that Zip the matrix conversions on the 2 remaining cooks. Okay, Kepler solver. Okay, so we're gonna need Kepler drift single planet R0V0 DT mu R0 mag. Okay, or this formula here. Calculate the gravitational parameter. G of M star plus M internal. Okay, we're gonna need that mu, I guess. Now we're going to calculate the semi-major axis A using the energy equation. This guy. And numerically solve. Okay, you know what? For this stuff I have not resorted to using AI, resorting to looking at the implementation. But here I'm gonna do that. Yes. Okay. Home. Rebound. Thank you. Source. Somewhere here it has integrator WHFast. Let's see. Okay, so this is a thing I'm gonna define here. So, so LSSRC. First, I'm just gonna commit transformations done. And if I git push this whole thing. Okay, but now let's ready for SRC. Okay, I have WHFast already in there. Okay, I'm gonna just open this. Yeah, I added a tiny. Yeah, just added a tiny little bit of a thing. So, particle store. Store particles. Yeah, and double DT. Okay, what do we have? You're gonna need all this mess. The mess of a data here. So let's ignore all that and only include what's necessary. So let's define a tiny helper. Let's just go for namespace. Unnamed namespace. So we have template. Type name T. I don't want to do macros right now. What's the T max, TATB, and the error, and it has to be this stuff, yeah. Return A less than B, if so, B otherwise A. And I'm just gonna one line this. I could probably one line that too. This whole thing too. So now if I yank this, but just call it min. Otherwise it's gonna be A or B. Okay, that's done. Next. So now this is WHFast create. Yes, and I don't know why it's undefined here. Let's ignore that. Whatever this is, like, it has been this code's recently been updated, so it's completely different. Let's ignore this monstrosity. Okay, documentation dot stuff dot synchronize dot create dot free. Create. Okay. First, we have our giant corrector table. Yeah, this is just gonna be. I'm going to speed this up in editing, so brace yourselves. Okay, that's done now. Our giant table of numbers. Now I'm gonna deal with I guess I'm gonna deal with inverse factorial, everything that's trivial. Yeah, basically everything other than ending with the Kepler solver. Okay, so we have a giant inverse factorial table. So, can I just, pull this line of code directly in here? So, static and now const. And I'm just going to const expert as a C++. Okay, so that's done. Okay, now we have static fast absolute value. Yeah, it'll probably format this in a better way, and probably wanted to do that, but what is it? So that's an inline fast absolute value. Against this 4. So if I go, it's a double fast apps. Return if x is greater than 0, so x other than negative x. Okay, and if I go to const expert, and now that's done. Wonderful. Static void stump CS. So all the functions, all the inner functions here are just gonna be. So I'm just gonna pull everything out from here, and I'm just gonna go up all the way to the end of this line. So D, I'm gonna put this whole thing above here. Okay. Now here, this is kind of important, and so void stump CS, and it's double restrict CS double Z. And so we unsigned int n equals 0 while fast abs Z is greater than 0.1. I don't know what's happening. We say Z equals Z divided by 4, and we increment n. And so const int n max is equal to 15. Expr, make that const expr. And if I double C odd should equal in factorial index n max double C even should equal in factorial index n max minus 1. And now we have this loop. So for int I equals int np equals n max minus 2. Now, if np is greater than or equal to 5, we decrement by 2. I don't know what that's to do, but... And now, np minus equals 2. And C odd is this. C odd equals index np minus this z times C odd. And even is np minus 1 minus c times c even. Yeah, okay. Okay. Okay, so we have CS index 5 equals C odd. It's a... Okay, I think I figured out why it's a pointer. It's an array. That's just slice into an array. I think I determined that. The CS index 4 equals C even. CS index 3 is in factorial 3. Index 3 minus Z times CS index 5. CS index 2 is in factorial index 2 minus Z times CS index 4. And CS index 1 equals in factorial index 1 minus Z times CS index 3. Now, for n greater than 0, n minus minus, isn't that an infinite loop? I don't know why that's there, but I don't know. Oh, now, you just have an infinite runtime, basically. I don't know what that is supposed to be, but... Okay, so let's... And now, Z equals Z times 4. Oh my, no, I think I... Go back up. Z is a... Z equals Z times 4. CS index 5 equals CS index 5 plus CS index 4 plus CS index 3 times CS index 2. And times 0.0625. And then CS index 4 equals 1 plus CS index 1 times CS index 3 times 0.125. CS index 3 equals 1 dot over 6 dot minus z times cs index 5 cs index 2 equals 0.5 minus z times cs index 4 cs index 1 equals equals 1 minus z times cs index 3. Okay. And so now cs index 0 is equal to in factorial index 0 minus z times cs index 2. Okay. No, okay, so now I have void stump cs3, and it again takes a cs and it takes in another double z. Okay. And we actually analyze this code. N equals 0, and it's not even changed like anything positive to this code. It just straight up does an infinite loop down there, which is weird, but yeah, maybe there's some terminating condition, who knows, that I don't see. Okay, so is there any difference between this code and that code? Oh yeah, there is. Okay. Unsigned in n equals 0. WHFast abs z is greater than 0.1. Z divides by 4 and n increments. And constant n max equals 13. So double C odd equals index n max. And that's looks very similar to the code above, but ever so slightly different. And 4 and NP equals n max minus 2. NP is greater than or equal to 5. NP minus equals 3. That's 3 here, yeah. 2, and here we say C odd equals in factorial index NP minus C times C odd. C even equals in factorial index NP minus 1 times z times is even. Yeah, this looks kind of similar, but it's slightly different. So C3 is C odd, C2 is C even. And C1 is n factorial index 1 minus z times C odd. D times n factorial index, no, not z times, just n factorial index 1 into minus z times C odd and then C even. And CS index 0 equals n factorial index 0 minus z times C even. Now for n greater than 0 minus n, and we CS index 3 equals CS index 2 plus CS index 0 times CS index 3 times 0.25 and CS index 2 is CS index 1 squared times 0.5 and if CS index 1 is CS index 0 times CS index 1 and CS index 0 is 2 times CS index 0 and then we squared minus 1. I don't know why it's not scaled, but I guess not. So now we just have two more functions, Stiefel GS and Stiefel GS3. So Stiefel GS, which takes in another double pointer. And what is the parameter name? GS with double beta and double X. And this double x2 equals x times x equals x times x. Stump CS and GS beta times x2 GS index 1 times equals x GS index 2 times equals x2 and oh, that's interesting. I don't know why that's why. I think it's because C standard library stuff, but double pow should equal x2 times x. And now GS index 3 equals times equals pow times equals x again. And GS index 4 times equals pow. Pow times equals x. And GS index 5 times equals pow. And we return. Even though that's literally the end of this function, I guess we return. Yeah, no, there's a whole bunch of code stuff in there that's weird. Default GS3. Double restrict GS. And I guess it's all the similar stuff. Double x2. x2 equals x times x. And we have stump CS3. GS beta times x2. And then we have GS index 1 times equals x. GS index 2 times equals x2. And GS index 3 times equals x times x2. Close enough. And we return. And we explicitly return at the end. Okay. And that's it. I think. Yeah, that is it. I guess now we're gonna end the video.